So, all right, I'll go ahead and start. Anybody have any questions about anything before we start? Nope. Okay. So unfortunately, this is kind of like a walk through history, as always. So, we're in the quantum mechanical model, and so we talked a little bit about electromagnetic radiation. And electromagnetic radiation, it's a transverse wave, meaning the motion is perpendicular to displacement, but transverse waves have perpendicular electronic fields and magnetic fields, all moving perpendicular to the displacement where it's moving. But it turns out that light is made of tiny particles called photons. And this was actually Einstein's discovery. Everyone thinks of Einstein with relativity, but he got his Nobel Prize, which is considered the highest prize in that you can get by the photoelectric effect. And the photoelectric effect is when you shine different frequencies of light on a metal surface, right? It is visible. It's usually ultraviolet. Of course, we can't see ultraviolet, but we can, or most of us can discern visible. And I have red over here, yellow, green, and blue, and then a more intense blue. And they found out was that for lower wavelengths of light, no electrons are ejected. You get to a point where electrons of light or electrons start to be ejected. And if you change the frequency, for higher frequency, the electrons move faster. And if you increase the intensity, you get more electrons. And so Einstein said, hey, that means that the electrons are bound to the metal surface, and then the binding energy, and then had the kinetic energy of the electron is equal to the energy of the photon, which is h nu, the Planck's constant, h, the frequency, minus the binding energy. So that's kind of considered to be common sense, like science common sense. Like it's how fast something is moving is how much energy you put in minus by how much it's bound. So why do we care? This led to proving about quantum mechanics. So even, well, kind of beyond the scope of the class, we have two theories that describe most of what's going on. We have quantum mechanics and we have general relativity. So before that, before the 1940s-ish, we had just classical mechanics, so Isaac Newton. And that, I mean, classical mechanics still work. You take lots of classes on it, you learn about it, and it describes many things. But if you start looking at things like orbits of planets and also how atoms behave, classical mechanics doesn't work. So we have, like I said, general relativity and quantum mechanics, and we're going to talk about quantum mechanics a little bit more. And part of it is that things exist in only specific quantities, like quanta, so items, numbers, and space-time itself. So we are in space-time, that's quantized, right? Because to go from one point to the other, if you move across infinity, it takes infinity time, right? So to go from point A to point B, it takes a little bit of time to traverse across something. And that means, though, that space itself is made of little tiny packets of existence. So that's like one of those really easy proofs. And everything else, little tiny existence. So, I already mentioned photons. And photons are different than atoms. And we'll talk about it probably next class or the class after, how they're different. They're bosons. Yeah, question.
So is it that quantum mechanics and general relativity, they don't match up, and we're trying to figure out why?
They do match up, but they describe different things. So what we can't do is we can't start with protons, neutrons, and electrons and come up with the orbit of Mercury. So we can't bridge the entirety of physics with you can't describe the entirety of physics with quantum, and relativity can't describe the entirety of the quantum world. So we don't have a grand unified theory. There are some candidates, but they're only mathematically, they're not experimentally proven.
Like string.
String theory, yeah, it's a math. There's many different types of string theory, It's mathematically proven, but it's not considered a valid scientific theory.
Because you can't test it.
Yeah, they're looking to see if they're trying to look for some things that are predicted by string theory, but not general relativity and quantum. So we'll see. Maybe in our lifetimes, who knows? There's a lot of weird theories. Well, I guess they're really hypotheses. So, okay, and light is like a particle. It's also like a wave. So if you look at light and you expect it to act like a wave, it will act like a wave. And if you and light also has particle-like behavior. So it has these quanta, these photons. So, and this is where we left off with photon energy. So I like this stuff so much more. I'm like, yes, quantum mechanics. So we have a nitrogen excimer laser that has 337 nanometers of or wavelength and 3.83 millijoules of energy. How many photons is this? Well, and the analog I wanted to have for you on this is like money. So if you have $20, how many $1 Snickers bars can you buy? And it's the principal, the amount of money that you have divided by the price. So if you have $20 and you're buying $1 candy bars, you can buy 20 divided by 1 or 20 candy bars, not surprising. So same idea with number of photons. If you have the total energy and you divide that by the energy per photon, so that's similar to how much money you have, your principal divided by the price will tell you how many items you can buy. So the energy divided by the energy per photon will tell you how many photons this is. And energy, so energy is equal to Planck's constant times the frequency. Speed of light is lambda nu. So this can be hc over lambda as well. So lambda being the wavelength, because you're given the wavelength there. So, and this is the energy per photon. The energy per photon, then this is going to be Planck's constant 6.626 times 10 to the minus 34 joule times second. Speed of light is 3 times 10 to the 8 meters per second. You don't have to memorize these, by the way. And then let's see, your wavelength, 337 times 10 to the minus 9 meters. That's a nano is to the minus 9. Okay, so that's the energy per photon. Your total energy is, so 3.83 times 10 to the minus 3 joules divided by the energy per photon. I'm just going to go ahead and copy this. And if you look at the units,
54 or 34?
34, did I? Oop, shoot. Is that hard to see? Yeah, it'd be pink. We'll have a pink 3. Is that better? Okay. So joules cancel, seconds cancel, meters cancel, right? So unit wise. And if you just put that in your handy dandy calculator, and I'm going to cheat and look at the answer. And it is going to be 6.49 times 10 to the 15.
Is it 3.37 or 3.37?
This is going to be 3.37 times 10 to the minus 7 meters. Right, so nano just means minus 9, 10 to the minus 9. So I can write it as 3.37 times 10 to the minus 7, or I can write it 337 times 10 to the minus 9. I guess 3.37 times 10 to the minus 7 is more proper.
Okay.
So, but if you put in your calculator, it'll figure it out. Why are you checking my work?
No, I just.
Yeah, you can. I mean, No, I'm glad if you're checking your work. It's active learning. It's great. I just, I used to plug these in my calculator as I taught, but now all the apps, they don't really let you show you the work anymore. And it would just be me. Yeah, I got that right. Congratulations, class. Like, congratulations, professor. So besides, I have a formative assessment following it, so you can see if you get it or not. So, other questions? All right, let's see if you can figure this one out. Laser pulse at 532 nanometers has a pulse of 4.67 millijoules. How many photons is this? So change the energy, change the wavelength. All else is the same. So H and C do not change. Speed of light doesn't change. Planck's constant doesn't change. How you doing, Zoomers? You doing all right?
Yep.
Sweet. Where's negative 3 divided by? Is anyone stuck and have no idea what the heck to do?
Just putting it in the calculator now.
It's really gluggy. So Rihanna, is your major computer science?
No, I'm, early college student, I don't have
Your what?
early college student, so I don't have.
Oh, okay. Oh, okay. I guess we don't even have computer science. We have ICS.
Like coding, we don't have coding classes.
We do. But we don't have a major computer science. We kind of do, but it's not exactly. Okay, so, all right, how many people think A? Okay, so that's more than half the class. A is the right answer. If you plug this in and go ahead and put in my calculator, I get 1.2498 times 10 to the 16 photons. So if you can't do that, please come talk to me because it's usually a calculator error. And if you can't put this in, then of the calculator error, it's actually usually order of operations. So that's where the most common mistakes are. So if you are having issues with that, come talk to me and we can play with your calculator and we can show you how to do it. So anybody have any questions with this? Awesome. Okay. Now moving on. Okay, as promised, we're going to talk about electrons. So we're going to move and no longer talk about light for a bit and talk about electrons. And there is so I know we're skipping quite a bit of physics here, but there's something called a de Broglie wavelength. And the de Broglie wavelength is Planck's constant divided by the momentum. So P is momentum. So the de Broglie wavelength of an object is Planck's constant divided by the momentum. And momentum is also mass times velocity. So Planck's constant h divided by mass times velocity. And so everything has a wavelength. We have wavelengths, but we're just too big. So, I mean, our wavelength just doesn't make any sense as far as the quantum world. It's too small. But something like electron is tiny enough, the wavelength of electrons, they can be observed and can be described. So what is the wavelength of an electron traveling with a speed of 2.65 times 10 to the 6 meters per second? So how we do this then, the de Broglie wavelength is Planck's constant times divided by the mass times the velocity. So 6.626 times 10 to the minus 34 joule seconds divided by the mass of electron. I think it's 9.11 times 10 to the minus 31 kilograms. Is that what it is? Let's see how nerdy I am. Yes, I got it. Nerd. Thank you.
You're welcome.
Thank you. And velocity, it's already given 2.65 times 10 to the 6 meters per second. So if you keep on studying science, you too can store interesting things like the mass of an electron in your head. Okay, and let's look at the units. A joule, as before, it's a kilogram meter squared per second squared. So dimensionality, kilogram meter squared per second squared times second divided by kilogram times meters per second. So this second cancels, the other second, inverse seconds cancel, meter cancels, kilogram cancel, and we're left with meters as the units. So we throw this into our calculators and we get 2.74 times 10 to the minus 10 meters. So, and first thing you think about is that's pretty small. So that's 200 picometers, 274 picometers. That's about half the size of a hydrogen atom. So that's to an atom, that's pretty big, right? So if you're in the atomic world and you see a wave that's half your size, right? Think of it, you're in the ocean. If you see a wave half your size, you're like, okay, I'm gonna feel this wave kind of thing. And if you're an atom and you see a wave half the size of the atom, This is something that you can experience. It's going to have something, an effect on you. Of course, to us, so 30 picometers is, oh no, this is, wait, this is the 300, no, 30. That's going to be, that's not going to matter for us. Actually, that's 300 picometers. I'm mistaken. So, yeah. Still, that's even bigger than atom. Oh, geez. So anyways, this is really small, obviously. And just to tell you some things about electrons are really weird. Okay, so if you study more and more about electrons, and in chemistry, in my mind, chemistry is really the study of electrons. So, right, I mean, like, why don't my hands push together? It's because of the electrons. They're negatively charged, and the electron clouds of both my hands, they push up against each other and they repel. And that's the reason why we have the repulsion force. If I rub them together, the electrons rub together and they heat up. So it's really, really all about electrons. And electrons, if you make them go really fast, they change their behavior. So like in a particle accelerator, so like if you have like something like a SLAC, the Stanford Linear Accelerator at Stanford, or a synchrotron. So those are particle accelerators. They're going essentially the speed of light. And then the electrons themselves, they become like really thin. They're like really long and thin, and they kind of stack up on top of each other like pancakes. So I guess I'll talk more about that later when we talk about orbitals and shapes and uncertainty. So electrons are weird, but it's cool at the same time. Okay, but that's how you do the Broglie wavelength. I've already wrote down the mass of the electron there. So let's see if you can do the switcheroo here. If let's give you the de Broglie wavelength and see if you can calculate the velocity from that. So now the wavelength is 1.2 times 10 to the minus 10 meters. What is the velocity going to be?
It's always the constant.
H, or what is
The mass of the electron.
for this application? Yeah.
So for photons, basically.
That's a complicated question. For this class, it's constant.
It's constant. I don't know that. There could be different.
As things speed up, their apparent momentum increases. So you could argue that electrons are becoming more massive.
Meaning like their energy turns into mass.
Turns into momentum, but it's, you can say it's mass. Because it makes sense because you're not changing the velocity, but it's kind of a fuzzy point. It's wibbly wobbly, timey wimey. Or do you know Doctor Who? Okay.
People say I look like him with this haircut.
Does anyone here watch Doctor Who?
Yeah, I used to watch all the Doctor Who. I don't follow it. I don't follow it anymore.
Yeah.
I'm weird now. All I know is there's like 13, 14 doctors.
Yeah, because they have a new one.
It's just a woman.
I haven't watched it in a while. I'm a casual Doctor Who fan.
It fell off.
What's that?
I think it fell off. I don't know.
Oh, okay. Do you ever see the Weeping Angels?
Yeah, I like that. I like that character.
That's because that's a quantum. That's a quantum character.
How does it work? What's the science behind it?
When they observe it, they're in a quantum state, quantum flux until they're observed.
Oh. What about the time travel stuff? Is that
It is, as far as we can tell, we don't think time travel backwards is possible. Forward, yeah. I mean, we're doing it right now. And you can slow down time.
Smoking that was kidding.
Well, I guess you can go back in time on really small steps, something called the Feynman diagrams. You can have certain things happen before the it's like a break of causality. You can have the effect happen before the cause, but only under really short time.
Is it like a quantum thing?
Yeah, it is. Like a photon can be emitted before it's absorbed.
Wait, and the photon was at the speed of light, because I've heard that we can't measure the speed of light just by itself. We can only measure the distance of it coming back, there and back. Because you can't have something send a signal to the computer of how fast it went, because the signal goes at the speed of light too.
I see your point.
So we only know like the speed of light squared, and we just square root it. I've heard. So like that's how maybe it could happen. Something could happen before it travels.
Oh, but yeah, but there's a fine point with the uncertainty principle. That's something. That's something different. It's not necessarily the measurable part. It's the uncertainty, which we'll get to. Okay, so how many people think A? How many think B? Okay. Actually, a lot of people, there's 3 that said B, and that's the right answer. Where are you guys getting stuck? We can set this up. So if lambda D is H over mv, and you want the velocity. So velocity is going to be H over m lambda, which is 6.626 times 10 to the minus 34 all over 9.11 times 10 to the minus 31 times 1.2 times 10 to the minus 10. So that's the numbers you should put into your calculator. Did you guys just need more time? I'm asking for feedback, guys. What is it? What's going on? You did the other one perfectly. This one you're a little stuck on. What's the answer?
I think I was thinking of the constant divided by the mass as a coefficient of x, which x is what we're trying to find.
Okay. So did you do the algebra wrong to start off with?
Yeah.
Okay.
So I ended up putting that all on the other side.
Okay. All right. Do you see your mistake now?
Yeah, and I still can't do the calculations. Plug it in.
All right. I'll show you after.
Can you show me your answer? Because I get the answer, but like the exponent.
Put it in the calculator. Oh,
I would something happen to us.
sure. Actually, I guess there's 2 of you guys. Why not?
So we can make it.
What's that?
I guess I'll do that.
Are you sure?
Yeah.
Is anyone else having a hard time with this? I mean, this is a good time to do it.
Yeah, we should do it right now.
Yeah, let's just do it now. Yeah.
After they workshop.
Yeah.
Oh, yeah, no. That's just
Okay, let's say I stole this then. But you don't have the number. That's definitely stolen.
I just agree and hope it happens.
I want what's the next year? Well, actually, this year.
Wait, really?
Yeah. Yeah, that was crazy.
They're only like 12 bucks.
I know, right? I think it's just like highly sought after.
Not this one, but, oh, yeah.
Graphic.
It's like,
Yeah.
this is aimed towards kids probably. So it's like, I don't know. Like, no, holy God. Okay, no, great. Okay, the 6.626. No, it's this one. You're the second. Yeah. One is 34. Just put. One.
On the graphic calculator, is it easier?
It's just bigger screen, you can see all those steps.
You can like move around and stuff.
Yeah,
You have a graphic calculator?
I do.
It's like a dude. Like, you know?
Right.
These guys know that.
I've had it for years. Oh, yeah.
Are you going to follow? Huh? I've been able to do it just type in. Let's see. Okay, so. Okay, so okay. You wanna come watch? Let's take a calculator. Okay, so if I calculated this, then it's 6.626 times 10. There's an easier way. There's an easier very much. Okay, you do 6.626. E minus 30. It's over X, and then there's one. So then it's second E. E. Did you say to do that? So, yeah, because you divided by that. Okay.
And then this one. Close it again. Wait.
Yeah. E.
Yeah, okay.
Yeah.
Just had to close it, that was it?
Yeah, it's a syntax error, right?
I mean, I think I did it. Here, let me do it again without closing it.
There's an easier way.
Oh, I don't know.
There's an easier way, you can use the E button, so can you do that, or?
Yeah,
Okay, let's see it. No, it's different, it's a psychomotor skill. Psychobrain, hand. You don't need the times, get rid of. So then it has its own number.
What's that?
It has its own number.
Yes.
Like that?
Divide by. Okay, I can see that. Because math always goes from left to right. So you did one number, you divide by another number, and then the parentheses means times.
Oh, so I have to equals and then.
You can put another division sign there, or you can put the whole, the denominator in parentheses. So you have to put the parentheses before the mass of the electron.
So yeah.
Yeah, and you can put insert middle. Negative sign. 31. Negative 10.
Oh, my God.
Sorry about that. So the way you did it before, because you had 6.626 times 10 minus 30 divided by 9.11 times 10 minus 31, and then you have the parentheses, which means times.
Mhm.
So, because in my thing, I had the numerator, I'm sorry, the denominator, they're separate. So my parentheses just has to be times. So if you do that, the math goes left to right, so it'll be like 6.626 divided by 9.11. That does that, and then it times it by 1.2. So then you
Okay,
get,
so the parentheses up ahead.
yeah, yes. You can also put you can do divide. That'll do the same thing as well. So I mean, it depends on how you want to. If you're confused by that, just do the parentheses of it.
Okay.
Does that make sense?
Yes.
Are you good?
Yeah.
Okay. Are you following? Or
I think so.
let's see.
So, my question is, when we look at just what should I multiply this first? And then
Andrew, right?
I'm not sure.
Andre, sorry.
But I
You can do it either way.
This is the,
I heard
I could be said, but.
Are you going to check mine?
You know that.
So I would do 6.626
Man.
E
We what?
minus 34 divided by quantity.
Sorry, I'm like.
We played it's like a Nintendo game.
Times 1
First, right.
10. Oh, that's weird. Oh, there we go.
Only
Okay.
because you say you're back.
And then we just.
Yeah.
You gotta leverage.
Yeah. And
And
that's,
you gotta
that's 6. Six.
Yeah.
Yeah, 6.
I always put myself to work, but I never played it.
Does that make sense? Yeah, that one's a little harder to use.
Yeah, I was just doing it by hand, like.
Yeah. You can do it that way. That'll work. Yeah, when you did it right. Yeah, so either way, I guess maybe why it's broke, why fix it? Just keep on doing what you're doing.
Cool, thank you.
I thought that's the calculator that's $100.
No, it's not. This is the one I found in my dad's drawer.
Wow. And you're good?
I'm good.
Okay. All right. So. Sorry, Zoomers, we don't get any love because I can't come to your houses and look over your shoulder. And then you can I showered before class, so hopefully I don't smell. So, but you guys have any questions? Oh, we got it in the chat. So Eli is asking, where does 6.626 times 10 to the minus 34 come from? That is Planck's constant. So that's like R. It's another constant. It doesn't change. So that's just Planck's constant H.
You think about it, God.
Sure, we can go with that.
So when I was in grad school and I was studying for my qualifying exams, I had a dream that I was playing football and the quarterback could change Planck's constant and the play was a spectrum. And depending on Planck's constant, then the spectrum changed. It was a very strange and technical dream.
Were you in football? Did you play football?
In high school.
That's fun.
But yeah, that's something we can't really tweak, though. That's just it's like trying to change gravity. So okay. So if there's no questions, we're moving on. So uncertainty principle, as promised. So this is also known as the Heisenberg uncertainty principle. It actually comes from linear algebra. So this is a mathematical thing that shows an effect in the physical world. So it's kind of interesting in that. So what really rules the world? Is it physics or math? It's physics, not math. But but the uncertainty principle, this is, so X is position, P is momentum, your uncertainty in your position times your uncertainty in your momentum is greater than or equal to H Planck's constant over 4 pi. Another thing is you might see H bar, you'll see H with a line, like a diagonal line through it. That's known as H bar. H bar is Planck's constant divided by 2 pi. So this can be described as delta X delta P is greater than or equal to H bar over 2, for instance. So
What does that mean, H bar?
it means H over 2 pi.
That's it.
Yeah,
Okay.
just another constant. So, or it's a combination of constants. So H and pi. So what this means is, what the physical effect of this is, that if you know your position really well, you have no idea what the momentum is. And if you know the momentum very well, you have no idea what the position is. So another way you can look at this is also with energy and time. So you see this with laser pulses. So if you have a really fast laser pulse, like in a femto or attosecond laser pulse, so really, really fast, the energy of the photons are varied. So, I mean, if you, for like a nanometer, or a nanosecond pulse laser, so you can get green light, and there's not enough, the timing difference is there's not really any uncertainty in the energy. But if you have a really, really fast laser pulse, you're going to have the energy of the photon is spread out. So I know that's an advanced topic, but you do see these effects. So that's another reason why you would never use femto or attosecond lasers for anything other than research, because like the photon energy levels are so varied. You can't use it for anything. It's not, like I said, it's not really anything you can do other than use it to study time. But there is a joke. So Heisenberg is speeding along, a police officer pulls him over. Police officer asks, Professor Heisenberg, do you know how fast you are going? He responds, I know where I'm at. Because with the uncertainty principle, if he knows his position, he doesn't know his momentum. So, oh, I gotta love the science humor. Okay, so so uncertainty. What do we mean by uncertainty? And this is where I say where electrons are weird. So electrons, they kind of exist in this. They have this kind of packet of existence, and their position and their momentum is varied. It's bound by a certain area, but where it's moving and where it's at is kind of fuzzy. And not only that, it's a certain case where, is it here, is it there? It's actually in all those places at once. So it's not like an electron is something that dances around. It just kind of fills this area. And that's because it has uncertainty in where it's at. So meaning, let's talk about classical trajectory. So what's something that I can't break? Here are my keys, right? So here is a classical trajectory. So I'm taking my keys and I'm throwing them across the classroom, Zoomers. So there's my keys, and it, you saw it go. So you threw something, you shot something, a cannonball, and it follows a path, right? And there's no question. There's no question of where this is going and how fast it's going. So, right, so we know where it's at all times, and we know how fast it's going. And that's because this thing, weighs, 20, 30 grams. So if you have something really, really small, like an electron or a proton or something like that, and you try to do the same thing, you get a probability distribution. And like where is this electron flying to? If I'm shooting an electron in like a cathode ray TV tube set. So as the electron is traveling, where is the electron? Well, the truth of the matter is, at least as it's moving, it's in all these places at the same time, because there is an uncertainty on where it's, especially since like something like a cathode ray tube TV set. How I say, well, we have LCDs now. The way the cathode ray tubes work, you have a tungsten filament and you run electricity through it, and electrons come off of the piece of tungsten, and you have these two plates. And you put a charge on the plates, and it shoots the electron off of the tungsten filament, and then it bends. And you take it and you put a magnet, and it bends, and then you have these little pixels. It's more like hexagons, and the electrons hit the different hexagons, and then it's red, blue, and green for the color of a color TV set. It's black and white, for a black and white TV set. But with a cathode, and the beam of electrons is called a cathode ray. So with a cathode ray, you're very certain on where it's going, on its momentum, because you have the plates and you bend it. So you're really, really sure the direction where it's going, but the position becomes very uncertain. And if you were to try and track the electron, it's what's strange about this, since you know the momentum well, the position is going to be varied. And it's going to be a case where is the electron then? And people think it's dancing around. No, it's not. It just occupies all those places at the same time. So, and another thing I mentioned with particle accelerators, when you have electrons that are going close to the speed of light, their uncertainty in their position becomes more kind of like linear, and they become like these really long, skinny pancakes. And they also don't repel each other very much, because the electron's position is so diffuse. And it's not like the electron, it just exists in a really long line. And that means the charge of the electron is spread out as well. So then the electrons are not very repelled by each other. The electrons, they almost stack, they don't exactly stack up on each other, but they get really close because of their position uncertainty, and their charge density just becomes very low. So, but I just thought it's kind of cool. Oh, and here's how the book describes it. So it's kind of like if you have for a major league baseball game, the pitcher tends to hit a lot of the baseballs around right here in the strike zone, but there's some straggling out. This isn't as good an analogy in my mind though, because the electrons actually exist through all these places at the same time, and it exists more. So, and we talk about the wave functions that'll hopefully make more sense. So, okay, questions so far? Yeah.
So does it really exist in all places at the same time, or is it just that we don't know because we can't look at it?
It really does exist in all places, and if we look at it, it changes.
Oh,
So if you yeah. So yeah. And let me move on, talk about the Schrodinger wave equation. So Schrodinger wave equation, I think I told you this story. Schrodinger went to a conference, and then he left and spent the weekend with his mistress. He came back with the Schrodinger wave equation. So, and the Schrodinger wave equation is H psi equals E psi. So H is known as the Hamiltonian operator. And I see you guys taking notes. This is actually a bit above and beyond the class, but when I was a student, I hated being told something and then told it was wrong. So I tried to tell you the truth as much as I can. I guess you're still in the beginning of your college careers. What to expect next is like, oh, what we told you, that was wrong. Oh, and that we told before, that's wrong. And finally, like, this is the truth. And the truth is we don't know what's going on. So that's kind of what it means like to be a student in the sciences. So I try to tell you as much as I can. I mean, within reason, because I want to inspire you and spike your interest, but I also don't want to make you feel so overwhelmed. You're like, screw this stuff, and I'm gonna switch to English or something like that, which is fine. It's a very noble profession, a very noble major. But okay, so what the heck is an operator? So Hamiltonian. So Hamiltonian is the operator on the wave function. And here are some operators over here, the plus, minus, multiplication, divide. Those are known as operators. So, right, if you have one number and you have the addition operator to the other number, the addition operator tells you to add the numbers. If you have the subtraction operator, it tells you to subtract them. This is kind of really fun foundation mathematics. What does a plus, what does a minus mean? And it's something we just do, we don't really think about unless you go on to further study math. So the Hamiltonian actually is the potential and kinetic energy of the electrons, and it operates on the wave function, and it spits out the energy level. So E is the energy levels, and you get the wave function back out. So, and this is a trick using linear algebra, and the energy levels are known as eigenvalues. So that's not, if you go on and you study math beyond calculus, you can learn this. So, and also, if you take the wave function and you integrate from -infinity to infinity of the wave function vector dotted with the wave function's complex conjugate, and you integrate d tau as all space. So if you do that operation over all space, you get the pictures we'll show you later. So but the truth of the matter is, like, so the wave function, when you have a wave function, like the wave function for the electron on my finger, like, well, this means that the wave function to the electron on my finger, the wave function exists in Jupiter. And the answer is yes, it does. But practically speaking, the electron doesn't stray more than a couple picometers from the nucleus of the atom. So this is kind of a math trick of sorts. Okay, but so this is the Schrodinger wave equation, and it's solved for the hydrogen atom, and you get the energy levels of the hydrogen atom is equal to this constant minus 2.18 times 10 to the minus 18 joules over 1 over n squared. And I'll talk about n in a second. This is also known as the Rydberg constant. Some people could say the Rydberg constant, Rydberg constant. So some things about electrons, and I'm sorry, I am going to talk a little over your heads this class. And this is one of those things where it'll make more sense later. It's going to bug you, and hopefully in the next day or two, it'll kind of sink in. So as I go over the model. So start off with electrons. So we say that a free electron has zero potential energy. So we have an electron sitting in space. It has zero potential energy. When you bind it to an atom, the electron loses energy versus free, and then we say the electron has negative potential energy. So this is just puts R0 as a free electron, and then we say bind electron has negative potential energy. It makes the math easier. So we could make it absolute. We could pick a value and then relate everything to that. But the problem is, then we'd have to do two calculations. So actually we'd have to, like, if we had a bound electron, we'd have to relate it to the other one. And the thing that makes the most sense to relate is a free electron. So actually this way it makes the math easier. So sorry, I just can see you guys blinking and like, what the hell is this guy talking about? When we start doing the calculations, this might make more sense later. And I'm sorry that I'm, not exactly explaining everything. It's just because my experience is it's better to go through it on one fell go. So I already mentioned here, energy of level n is the Rydberg constant 1 over n squared. So what is n? N is the principal quantum number. So here we are now in the quantum mechanical model. N is the principal quantum number. And this epsilon and epsilon exists. The principal quantum number are the whole numbers, the positive whole numbers, non-zero, 1, 2, 3, 4, 5, on to infinity in steps. Okay, so whole numbers, not zero, is the realm of the principal quantum number. Then the next quantum number that we have is the angular momentum quantum number. The angular momentum quantum number, it can be integers. So it's positive integers, including 0, but it's bound by up to n minus 1, n being the principal quantum number. So now you set the principal quantum number, now you can set the angular momentum quantum number. And we have specific terms for the angular momentum quantum number. When L, the angular momentum quantum number, is 0, we call that an s orbital. So we'll come back to these later. We use the word orbital, something called the Bohr model. The Bohr model, they thought that electrons were orbiting the atom like planets orbit the sun. So they don't, they kind of have this fuzzy existence. But as a tipping of the hat to Bohr, we call the levels orbitals. And so for angular momentum being 0, we call that an s orbital. If it's 1, if L equals 1, we call it a p orbital. For L equals 2, we call it a d orbital, and L equals 3, we call that an f orbital. And I'm telling you this now because it has to do with how we shape the periodic table. What does SPDF stand for? It's spectroscopy terms. S means sharp, P means principal, D means diffuse, and F means fine. So those are the original SPDF, where it's sharp, principal, diffuse, and fine. So we don't really use that anymore. S is not spherical, P is not perpendicular, it's sharp and principal. So, okay, now we're going to move on, and we're going to have the magnetic quantum number. The magnetic quantum number exists to integers of L. So it can be minus L plus 1, up and through 0, then integer steps up into L. And so this one here, and I'll start showing you some diagrams. This one here will then tell you for an s orbital, you can only have one, m sub L can only be 0. So if n equals 1, L can be 0, that's the only option, then m sub L has to be 0. If n is 1, if n is 2, L can be 0 or 1. So n minus 1, so 2 minus 1 is 1. So L can be 0, 1 for n equals 2. So if L is 0, m sub L can only be 0. If m sub L is, L is 1, m sub L can be minus 1, 0, or 1. And if L is 2, well then n has to be 3 or higher. So for n is 3 or higher, L can be 2. If L is 2, m sub L can be minus 2, minus 1, 0, 1, and 2. If L is 3, for n equals 4 or higher, L can be minus 3, minus 2, minus 1, 0, 1, 2, 3. So, and that's where the periodic table comes in. We'll make that connection. Oh, I might as well tell you now. Why not? So sorry, Zoom, this is where you're not gonna, I'm pointing to the far left here. This is the s orbital. Okay, so these are the s orbitals, and there's 2 electrons in each, so this is 1. And I'm now pointing to the far right where the nonmetals, this is the p block. This is L is minus 1, L is 0, L is 1. And then these are the d orbitals. So there'll be 5 of them. -2, -1, 0, 1, and 2. And these, the lanthanides and actinides, are the F orbitals. There's gonna be 7 of them. -3, -2, -1, 0, 1, 2, 3.
Why do we do the minus?
It's just a way to keep track of the numbers.
Doesn't make
It means nothing.
it's not like a math equation.
No. No, it's a way, it's a model, and it's a way to have describe the quantum numbers.
Okay.
So it doesn't, the negative sign does not have any practical effect on the forces. Okay, and the last one, and if you read the textbook, we don't talk about this till next chapter. The last quantum number is the spin. And for electrons, it's +1/2 -1/2. So, and again, we learn about this next chapter, the Pauli exclusion principle. So the Pauli exclusion principle says no two sets of fermions, and then the book says electrons, no two electrons may have the same quantum numbers in the same atom. And so what are fermions? Fermions, and this, if you ever heard of Fermilab or Enrico Fermi. So fermions are a ratio of two integer spins that are not integers themselves. So, like 2 over 2 is a ratio of two integers, is also 1, right? So, but that's also an integer itself. But 1 divided by 2 is a ratio of two integers. That's not an integer. So that's a fermion. So that's an interesting thing about spins. So what the heck is a spin? The spin is the projection of the magnetic field at any given moment. So remember I told you that electrons have this fuzzy existence. And so if you have an electron, it's kind of fuzzy where it's at. And because it's negatively charged, it has an electronic field, it's a magnetic field. And the magnetic field is going to be pointing in many different directions. But if you sum up all of the magnetic field of an electron at a given time, it points in a specific direction. And that's the spin. So if you have spin +1/2, it's pointing this way. And if you have spin -1/2, it points the other way. And when you have two electrons, so when you have orbitals, you can have two electrons in the same orbital, but they need to have opposite spins. So they will always be, when they move, it's easier if they will always be opposite. Question?
And so that's why it's 1/2 -1/2, so that when they complete like one slot, like I remember from the orbitals, it's like one's up, one's down.
Yeah, because they just point the other way.
Okay.
The magnetic fields cancel. So, but you can have them add. That's another thing.
You can do 1 and 1.
Yeah.
Oh,
That's something called a Bose-Einstein condensate. You can make a boson from that. So, so particles that have ratio of integer spins, these are known as fermions. Electrons, protons, neutrons are fermions. So bosons have integer spins. So meaning 1, 2, 3, on up. So bosons have integer spins. So the Pauli exclusion principle says no two fermions may have the same set of quantum numbers in the same atom. Bosons, though, do not have that rule. So bosons can effectively occupy the same space at the same time. I mean, I know I mentioned that that electrons can be, and when you have two electrons in the same orbital, they are in the same space at the same time, but their magnetic fields are there. Jeez, okay. There we go. they cancel each other out. So, but you only have two. But if you have a boson, you can have as many as you want in that single state. So that tells you something about things. So light and energy, those are bosons. Photons are bosons. So you can put as much energy in the same point as you want. Whereas matter, well, at least most matter, so protons, neutrons, and electrons, they can't. So, and that's the other reason why we have this. This is the reason why matter has structure. Energy doesn't have structure. Energy is made of bosons. Matter is made of fermions. Matter has structure. What do I mean matter has structure? I can't put my hand through this handy white bucket. right? My hand will not collide through this handy white bucket. Why not? Because my hand has electrons and this has electrons too. And in order for my hand to go through this, the electrons in this orbital has to go with electrons in this orbital, but Pauli exclusion principle will not allow that. And then because of that, right, you get the normal force. You push up against it and it pushes back. That's also, I guess you're in astronomy, that's also known as electron degeneracy. So have you talked about that in astronomy yet? Okay. I don't know if you're gonna talk about that at all, actually.
We're on the main sequence stars. So you guys are like talking about the same stuff. Pretty interesting.
Yeah.
Spectrum.
Yeah, so this is what this explains why matter has structure and things like energy do not. And also, if you ever wondered how could the Big Bang happen? So that's how can we put all of the energy, all the matter and energy of the universe into one single point? Because a boson makes perfect sense. You can put everything in one point as long as the spins are integers and not fermions, not ratio of two integers. So although there are certain things I mentioned about Bose-Einstein condensates, so that's when you have matter, certain nuclei, you can get to have the nuclei, the spins can add up to 2 integer spins, and actually 2 electrons. 2 spin 1/2 added together can form a spin of 1. And we believe that's how superconductors work. So a superconductor is something that electricity flows without resistance. So do you know about those wires that there's a resistance in wires? Do you know about this? Do you know what resistors are? Okay, it's friction. So electrons are negatively charged and you start bringing a bunch of negative charge next to each other in like a wire. They rub up against each other and it turns the electrical energy, the potential energy from the wire, moving the energy going through the wire, it turns it into heat, turns it by friction, turns it into resistance. Yeah.
Does that have anything to do with the specific heat of gold and copper and silver?
No.
Okay.
No, it just has to do with the just how easily electrons flow there. For some reason, silver is the best. But but you can have 2 electrons, and if you get them in the right state, they can turn. And we don't really understand this. It can turn into a boson. And then we think they just condensate. They condense into a very dense form of matter, and they just flow without any resistance. So that's what we think is happening. And we also, generally speaking, you have to get them cold. Okay, so integer spins. All right. So your faces. Is this the face of worry?
Someone logged out.
Yeah. Oh, I'm out of here. This always happens. Whenever I teach this section, and the students are like, it's the O. I'm going to pick a letter of the alphabet, F. It's the OF face, right? So, and that's okay. And again, I'm not trying to talk over your heads, but you kind of have to let it hit you really hard at first, and then you start to think about it and like, okay, it'll start to make sense.
Do you think it's because we've only been taught like general relativity, like mass, it's like physical stuff?
Well, that's classical mechanics. So you've been taught continuous mathematics. Now we're talking about discrete mathematics. And not only that, I talked about an operator. Like you don't think like, oh, I just add things together. You don't think, oh, this number has an operation that I'm doing, an operator. Do we still have operators? I guess maybe you could call Home Depot, I guess.
I know 911 has an operator.
Yeah, that's true. Okay, so it's a weird way of thinking. Okay, and I'll just go ahead and solve this part, and I'll come back and talk about. I'll restart with the quantum mechanical model. This is the quantum mechanical model right here. The N, L, M sub L, and M sub S. This is the model. I've just presented you the quantum mechanical model of an atom.
That's it?
Yeah.
Anything?
Well, I mean, then there's
Really
that's the model, and then we'll talk about what it means. All right, class is over. I'm just kidding. That's not. Go about your lives. You've learned all chemistry. No, let me show you some of this, and then I will do this again on Wednesday. So what are the quantum numbers and names of the orbitals in the n equals 4 principal quantum level? How many n equals 4 orbitals exist? So, okay, so if n equals 4, so m sub L can be, it's up to n minus 1. It can be 0, 1, 2, or 3. So it'd be 0. Maybe I'll just go ahead and explain it, and I'll just erase it. If n equals 4, oop, where did that go? It disappeared. It reappeared. So if n equals 4, so L is bound by 0 steps up to n minus 1. So that means L can be 0, 1, 2, or 3. So, right, you got that from up here. Oops. So L exists up to n minus 1, and if n is 4, L can be 0, 1, 2, or 3. So for L equals 0, m sub L has to be 0. That's the only choice we have. If L equals 1, m sub L can be minus 1, 0, or 1. For L equals 2, m sub L can be minus 2, minus 1, 0, 1, and 2. And for L equals 3, m sub L can be minus 3, that's a looking 3, minus 3, minus 2, minus 1, 0, 1, 2, or 3. And when L equals 0, this is an s orbital, and it's specifically the 4s orbital. When L equals 1, this is a p, so this is going to be 4p. L equals 2, this is going to be 4d, and then this one is going to be 4f, because L equals 3 is an f orbital. And how many orbitals exist? So there's one 4s, so this is 1, and there's going to be 3 here. So we have 1 here, 3 here, 5 here, and 7. So it's going to be 1 plus 3. Geez. 1 plus 3 plus 5 plus 7. So let's see here, 8 plus 8, 16. So we have 16 orbitals. And there's another thing, the number of orbitals from a principal quantum number is also n squared. So you have 16 orbitals. You can fit 2 electrons in each. So you can fit 32. So 16 times 2 is 32. You can fit 32 electrons in the n equals 4 shell. And that's actually also from the Bohr model. Bohr noticed that the shells exist by 2n squared, the number of electrons in each orbital. Okay, so I'm actually going to go back and go over this again on Wednesday. And I'm sorry to have your brains be so painfully hurting right now. But like I said, it happens every semester, and and it gets better. But this is fun though, isn't it? I mean, it may be a little uncomfortable. Like sometimes learning is a little uncomfortable, but it's fun.
A lot.
Yeah. So sleep last night and all this. Yeah, man, it's Harry Potter. This is Harry Potter. It's magic. So all right, I guess I'll stop recording.